Imagine you're tasked with building a feature for a B2B analytics dashboard. The requirement is simple. Calculate the days until next traffic spike across 100,000 individual days of server logs. The intuitive approach works forward. The algorithm starts at day 1, scanning day 2, day 3, and day 4 for a larger number. But for day 2, it redundantly rescans day 3 and day 4, the exact same logs it just checked. In computer science, this is known as the worst-case O of n squared time complexity. At this scale, the workload increases quadratically. If you increase the logs by 10 times, the processing requirements increase by a factor of 100. Under the weight of 100,000 logs, the overhead becomes too much to handle. The CPU maxes out, and the user interface completely freezes while waiting for the calculation to finish. This shows the core flaw of the eager approach. By forcing every single day to independently search the future for its own answer, the system spends more time rescanning old logs than processing new ones. True efficiency requires letting the answers arrive on their own time. Instead of searching forward, we can process the timeline in a single pass using a monotonic stack. You can think of this as a deferred resolution waiting room. If today's traffic doesn't provide an answer, the algorithm stops scanning. It pushes yesterday's data into the stack to wait. But there's a trick. Instead of storing raw volume, the stack stores array indices, coordinates like day 0, day 1, and day 2. Storing the raw value only tells you what the problem was. Storing the index preserves the positional context, allowing the algorithm to calculate the exact distance between two events if it's ein vinyl set. This makes the index a more robust design choice. It gives the algorithm dual access to both the value of the spike and its specific location on the timeline. This waiting room follows the inverse duality principle. Because we are searching for a greater element, the stack naturally maintains a strictly decreasing trend from bottom to top. Every index inside is effectively waiting for a value that breaks that trend. This continues until a massive traffic spike finally hits the timeline. As the new spike arrives, it compares itself to the top of the stack. Because the new value is greater, the waiting day is instantly assigned its answer and ejected from the room. This creates a chain reaction. This single spike moves down the stack, resolving and popping every waiting day it surpasses in mere microseconds. By strictly organizing the unresolved data points, the algorithm allows a single new event to clear a massive backlog of queries in one rapid linear sequence. When you look at the final code, there's a glaring paradox. The algorithm features a while loop nested directly inside a for loop. Usually, a loop inside a loop is the signal of the O of n squared bottleneck we were trying to avoid. To understand why this is different, we have to look at the mathematical proof called amortized analysis. Track the life cycle of a single data point. An index in our dataset can only be pushed into the stack exactly once, and it can only be popped exactly once. Once removed and the answer recorded, that index is never processed again. Even if the inner loop processes 10,000 days in a single burst, it's only clearing items that were previously ignored. Across the entire array, the total number of operations will never exceed 2n. True linear efficiency isn't achieved by avoiding loops, it's achieved by ensuring no single piece of data is ever evaluated twice. It transforms 100,000 data points with absolute, instant precision.